Welcome back. So we've started talking about energy and the different forms of energy. And remember that we said that all energy is simply the capacity to do work. And we said, well, okay, what's work? Well, work is that exchange medium. It's how we're converting from one type of energy into another type of energy. And we derived a formal equation that could give us a definition for work. So we find that. And then if you remember, we took that definition, which was a path-dependent integral, and we were able to rearrange it in different ways to get different expressions. So for example, we found an expression for the kinetic energy, the amount of energy of motion. What we're going to do from here on out is we're going to start working on different types of energy. And in each case, we're going to derive a mathematical expression for it. And the technique that we're going to use is the same one we've been using all along. And it's the same one we're going to use over and over and over because this is how it works in the real world. Once you've got these expressions, though, you should create a page in your flipbook for each one of these categories, because the way we're going to solve a lot of these problems is just to simply write down all of my initial energies of every single type I could think of, and then that's going to be equal to the final. And then I'll mark out any of the ones that are zero or aren't present. Take my flipbook page that has the equation for that particular type of energy, 1/2 mv squared, for example. Write it in there, solve the problem, and I'm done. All right, let's get started. Okay, so up to this point, we've really only had to deal with one kind of energy, and that was kinetic energy. And while we talked about how there were different types, we didn't really talk about how those types were classified. Some of this you may know, some of it you may not, but basically any kind of energy that is an internal energy. So it's something that is inside the robot or whatever. Generally, that's going to be a reversible type of energy. What we mean by that is, for example, if I have kinetic energy, and then today we're talking about gravitational potential energy, I can convert that into gravitational potential energy. But then I can also take the gravitational potential that comes out and convert it back into kinetic energy. So in this way, we can trade that energy back and forth and we don't lose anything. So this internal energy or reversible processes that we're talking about then, you don't lose any energy. You can just swap it back and forth all that you want. Now, there are other kinds of energy. We've talked about the work done in bending the robot, those deformational energy, that energy of deformation. Those you don't get back. So, if I bend my robot's bumper, it's not going to just spontaneously come back, nor if I do bend it back, am I going to be able to get any energy out of it. In fact, if it's bent and I try to bend it back, I have to put energy into it, don't I? So that's called a dissipative loss. So that's called a dissipative form of energies because the energy dissipates. It's not reversible. Once it's in there, once I've spent that energy, it's gone. I can't get it back. Another typical example is friction. So if I have, some cars moving or something's rubbing against a surface, that energy gets converted into the potential kinetic energy, whatever it is, gets converted into thermal energy, into that work done by friction in there, and I can't get it back. So that's a non-reversible process. What we're going to be talking about here are internal forms of energy. And if you think about it, that deformational energy, it came from somewhere else, right? So we're going to figure out what we mean by gravitational potential energy, but then we're going to see how we can convert at any point, as in the robot's motion, I can see, okay, if this is what its kinetic energy is, then as I climb, for example, I can convert that into gravitational potential energy. And then as the robot comes maybe back down the hill, it can convert that gravitational potential energy back into kinetic energy and get some motion. So this is a very powerful technique because it allows us to effectively solve kinematics problems with just one equation and no vectors. So you're going to like that a lot. Anytime you can use energy to solve a problem, you want to. It's always going to be the easiest way. Now, we mentioned previously there are times when you can't use the energy method. So for example, if I want to know the time it takes for the robot to come down that hill, energy can't tell you anything about time. If I want to know anything about vectors, energy is a scalar. I can't tell you anything about the vectors that are going on with that. So in that case, we don't have a choice. We go back to kinematics, assuming it's constant acceleration. All right. So keep these strategies in your mind. There's not one way to solve a problem, but there's often an easier way to solve the problem. And a good engineer is a lazy engineer. All right, so take a look on the first page of the section here. And so we've got this mechanical energy that we're talking about. So that's like kinetic energy. But if you think about it, if I pick up my rover, I pick up my robot off the ground, and we've mentioned this briefly before, but I pick it up off the ground. Is it moving? Does it have, I'm just sitting there holding it. Does it have any kinetic energy at all? No, it doesn't, right? It's not moving, so V equals 0. Now, if I were to let go of the robot, what's going to happen to it? I'm not going to push it. I'm not going to do anything. I'm just going to let go of it. It's going to fall, right? Well, as soon as it starts moving, does it have any kinetic energy? Sure, right? It's got some motion. It's got a velocity. So that's happening. Well, that energy has to come from somewhere, which means that when I did work from my body, in this case, maybe with a rocket engine and an actual spacecraft, but if I did work raising this pen up or my robot up, I must have put energy in there somewhere. Well, that's my potential energy. That's my stored energy. And so the energy that I stored because I was doing work against gravity is my gravitational potential energy. So we're going to talk next time about elastic potential energy, and we're going to talk about how, if you take a spring and you compress it, well, the work that you did compressing the spring is now stored in the spring as elastic potential energy. Here's the thing though. If I pick that up and I let it go, I can get that stored energy out. Now I'm getting kinetic energy, but remember that I can't create or destroy it, any energy. So what's happening to my gravitational potential energy as that robot falls? It's getting less. So my total energy, my system energy, is conserved. It's the same, it doesn't change. And that's going to be the secret to the whole method. So if I know that I've fallen this amount of distance, if I know how much my gravitational potential energy has changed, that must equal the kinetic energy of the robot at that point. Well, if I know the kinetic energy, I know its velocity. So rather than using kinematics to say, okay, I've fallen this distance, and I know that my vector is here, and I know what the acceleration is, and all that other sort of stuff, I can do this same problem simply by saying, okay, I know how much my potential energy changed, my gravitational potential energy changed. That is my kinetic energy. Multiply by 2, divide by m, take the square root, all that sort of stuff, and we're going to be fine. Okay, so we need to have an expression, a mathematical expression for the gravitational potential energy, and that's what we're going to do here. Just like always, we're going to think about, are these quantities directly proportional or inversely proportional? This is what you want to be thinking about anytime you're looking at a new situation. Even if you know what the equation is, check your work. Does it make sense? As this quantity goes up, should this quantity go up? If they're directly proportional, then that quantity should be in the numerator. It should be on the top of any fraction bars. If it goes down, if they're inversely proportional, so say this one goes up and then this one goes down, then it should be in the denominator of any fraction that's there. All right. So take a look at your gravitational potential energy. Take a look at microtask 1. It says, is gravitational potential energy, we're calling it GPE for now because gravitational potential energy is way too many words to write out. Is it directly or inversely proportional to the height? So what you want to ask yourself is, as I increase the height of my rover, my pen, whatever I'm working with, am I storing more energy or am I storing less energy? Pause the video, think about it, make a choice. Remember, pause the video. You really do need to. It's important that you commit to these. That's what's helping secure it in your long-term memory. So the whole class gets easier if you actually commit, pause the video, make a decision, and write it on the page. That's where that long-term memory transfer comes in. Okay? It'll help you so that you won't have to study quite so much. Okay, so sure, as I pick this up, right, I must have more energy stored into it. The reason I know that is because I had to do more work to get it up. Because remember we said that the work also depends upon the distance that I've moved it. If you don't remember this, go back to the section on work so that you can see it. Well, I applied that lifting, that oomph, over that longer distance. So therefore, I've put more work into it. And remember, work is just the exchange medium of energy. So if I've put some work into it, that has now become stored energy. So the answer then is it's going to be directly proportional. So they're going to go like this, right? As I lift it higher, then I'm going to have more energy stored. All right, so what are the units of height? Well, there's a bunch of units you could use, right? You could use feet, you could use meters, you could use centimeters, you could use kilometers. Sometimes we'll use all of those. Remember that when we're working with units, with fundamental units, we always want to use meters, kilograms, and seconds. This is called the MKS system for obvious reasons. So always, always, always convert everything to meters, kilograms, and seconds. That way, if all of your equations are in that form, you won't make the mistake of using the wrong units with one equation. All right, so what are the SI units, the system international units, for height? That's going to be the meters. So let's write that in here. So that's meters. All right, and we need to come up with a symbol for every quantity. You choose, it can be anything you want. Common choices are Y, X, or H. I tend to like H just because it's the height, and that symbol says height to me. You know, if I'm talking about X or Y, as we've seen, sometimes X is on the vertical axis. So there's no guarantee that Y always means vertical or X always means horizontal or anything like that. So you'll usually find it better to use descriptive terms, descriptive symbols like this, where H is the height, whatever that is. So I can orient my coordinate system anywhere I want, but H is going to be my height. Okay, so now we need to think about what else it's going to depend upon. Okay, so the suggestion here is, if I've got a big heavy rock and I've got a light rock, which is going to take more effort to roll up a hill, or just even to pick straight up? And by effort, that's going to be a measure of how much work you're doing. Which one is going to require more work to lift to that same height? They're going to go to the same height, but I've got a big heavy one and I've got a small one. Pause the video, think about it. Well, it should be the heavy rock, right? So it is definitely going to be the heavy rock, and you've experienced that all the time, right? Light rock's really easy to pick up. We're keeping the same height. This is an important part of coming up with these equations, is you're only changing one variable at a time. So with the first part, we were saying, okay, I've got two things that are exactly the same. I lift one to a higher height than the other, then that means that I've got more energy stored in this. Now we're going to take two different objects, a big one and a small one, and we're going to raise them to the same height so that I'm only controlling one thing at once. And now you should see that, yeah, the heavier rock is going to take more work. So what quantity of a rock determines if it's heavier or light? Not a trick question. It's mass, right? So you may have said weight. That's not actually wrong. However, weight also depends upon how much gravity there is. So your weight on Earth is going to be different than your weight on the moon, which is going to be different than your weight on Mars, but your mass is going to be the same. And what we're going to find, this is just a preview as we start to talk about gravity, we're going to find that your weight is nothing more than your mass times whatever the local acceleration due to gravity is. So if you're on Earth, that's 9.81. If you're on the moon, it's like a sixth of that. If you're on Mars, it's about a third of that. Something. Okay. So for now, though, we're going to assume we're on Earth. But the thing that really matters is not the weight, it's the mass. And if you think about it, that has to be true. And this is even true if you're way out in space, in deep space, and you are nowhere near any kind of gravitational source. If I want to get something moving, if I want to give it some kinetic energy, it still has mass. And so just the fact that there's no gravity, it has no weight if there's literally no gravity there. So it still, though, is going to take work to get that moving, because even though it doesn't have weight, it still has mass. Okay, so as always, now that we've defined our quantity, we need to decide, is it directly proportional or is it inversely proportional? Stop the video and think about it. You got it? Okay, well, you decided that if I have a heavy rock, it takes more work to lift it to the same height. The more work I do, the more energy I'm storing. All right, so I've picked that rock up and now I'm storing more energy in it. So that means my gravitational potential energy is going to be higher. So as the rock goes up, the mass of the rock goes up, then the amount of gravitational potential energy goes up. So that's directly proportional. All right, what are the units of mass? Again, meters, kilograms, seconds. Those are your only choices. It's going to be kilograms. And we need a symbol for that. And I think most of us will agree that M is a pretty descriptive symbol. Now, be warned, you're actually going to use M for a lot of different things in physics. And you're going to hate it, But the reason for that is we simply run out of symbols. So that's why in your step 3, you always want to write out what the symbol means in English, because M here may mean something completely different. It could be something called a moment later. We also use a lowercase m for that as well. So make sure that you're defining your symbols in English so that everybody knows what you're talking about. All right, so far we have found that our gravitational potential energy depends upon the height and the mass. Now, this is all very easy, very straightforward, but what I'm stressing here is I want you to think about the physical reality. The energy has increased because it takes more work to get to that point. All right, let's flip over and go to the next page then. Okay, so now are we done? Is that it? Well, we kind of hinted a little bit before that something about the gravity is going to matter. Well, it's gravitational potential energy. You would think that that would come into play, right? But what about gravity? You know, is it the weight? Could be. So here's where we're going to apply our technique of dimensional analysis. Dimensional analysis just means I figure out what the fundamental units for any particular quantity are. And remember that we said that whatever units I have on one side of an equation has to be the same as on the other side. If not, it is wrong. There is no other way to fix that. So if we want to find out, our first step then is just find out what are the units of gravitational potential energy. Well, any kind of energy must have the same units because they're energy, right? So we can find any expression that uses energy or work, right? Because work is also a kind of energy. It's that change in energy. Any equation we want, literally doesn't matter what it is. As long as it's energy, we can look at that, at the symbols that are in that equation, and we can figure out the fundamental units for that. So the only kind of energy we've talked about so far, formally, is going to be kinetic energy. So our kinetic energy is going to be 1/2 mv squared, right? So in this space down here, we want to take each one of the symbols that you see in the expression here and write out its units. Now, the constant here, 1/2, doesn't have any units, so we wouldn't put that in there. What are the units of mass? Kilograms, right? So it's kilograms times, and then this is the units of velocity, or what? Meters per second, but I'm squaring it, which means I have to square both the top and the bottom. So that means it's going to give me meters squared per second squared. Do you see why? Because meters per second squared, you have to square both the top and the bottom when you do that. And be very careful because a lot of students will forget to square the bottom. That's usually what happens. Okay. All right, so those are the fundamental units for my energy. It's kilogram meter squared per second. Now the SI unit of that we've talked about before is the joule. So 1 joule, remember we said, was 1 kilogram meter squared per second squared. We've been through this kind of derivation before. So here's what's new. I know that gravitational potential energy depends upon the kilogram, right? Because it depends on mass. And I know it depends upon the meters. It depends upon the height, right? What's left? And by looking at the units of what's left, you can figure out what the missing symbol is. So I'm going to write this out right over here to the side. So we know we have kilogram meters squared per second squared. So this is the units of gravitational potential energy because it's energy. So we know that there's an m, which is going to be in meters. Actually, let's put it over to the other side so everything's in the same space. So we know that we have a mass, let's write it out, and that's going to be kilograms. And we know we have a height, and that's going to be in meters. And we chose the symbol m for this and the symbol h for that. You see why using that m can sometimes get confusing, right? All right, so this kilogram then is taken up by the mass. So I know I'm going to have a mass, all right? And m here means mass, not meters. Now this meters squared, though, well, a height is not squared, it's just meters. So I only have one of those right now. If I squared my height, that would give me meters squared, but I don't have any quantities that are seconds squared. So there's a little bit of a game here. Do I want to raise my height squared? If I do, then I've got to come up with some sort of 1 over time squared sort of thing. Well, that doesn't really exist. So let's start out with what we've got here. Just put it to the first power. And then what's left, so this is one of my meters, so that's going to get rid of this. I'm going to be left with meters per second squared. Right? And so that's what goes here. So those are the units that are left. So whatever other quantity, I know I'm going to have the mass, I know I'm going to have the height, and I'm going to have some other quantity that has units of meters per second squared. And this is what we do in the real world. We figure out, okay, what's missing? And then that tells me physically what else must be in my, in this case, gravitational potential energy. So what physical quantity has units of meters per second squared? That's the acceleration, right? So this must be the acceleration. So we know that then I must have an m, an h, and then an acceleration. Well, we have to, is the gravitational potential energy directly or inversely proportional? Here you can actually look at the units. You see that if this had been in the denominator, I would have had something like this, right? That would mean that my acceleration would go down here. But I don't, it's actually upright. So in this case then, I can just put, an A. So that A means acceleration. Does that make sense? So I know that my gravitational potential energy then, which we haven't defined a symbol for yet, must be m times h times a, where a is some acceleration. Okay, so now ask yourself then, what is causing that acceleration? Well, it's in the name, right? Gravity is the acceleration. So what symbol do we use for the acceleration due to gravity? It's g. Now I want to stress, you absolutely can use A. You can use Q, you can use smiley face, you can use anything you want. As long as you define it in English first, you can use whatever you want. And this is actually sometimes very useful because what if I'm on another planet? You may assume that G always means Earth's gravitational acceleration, which might be 9.81 meters per second squared, right? Mars, it's going to be less. However, we traditionally use that symbol G. So we would say that GPE is going to be the mass times the height, so there's my kilograms and my meters, times my meters per second squared. All right, and so this gives me units of kilogram times meters per second squared, or kilogram meters squared per second squared, which is a joule, so it's energy. You see how we do that? And the G there communicates, hey, this particular acceleration is due to the gravity of wherever I am. And remember that G is not actually a constant. We think that it is. We treat it like it is, but it's not. The difference in G actually gets less and less and less the further you go away from the planet, but it decreases very slowly. The difference between your ceiling and your floor is not enough you could ever hope to detect. And even if you get all the way up to the height of the International Space Station, which is considerably higher than our normal shuttle operations, the International Space Station is about 89% of what it would be here on the Earth's surface. So it doesn't change much. So unless you are actually launching rockets into space and you're doing orbital mechanics, in which case we have to define gravitational potential energy in a different way, here we can treat G as a constant and everything is good. All right. Okay, so let's go over to the next page then. So in microtask 3 then, we're going to write out our final form. Now, before we wrote down MHG, because that was just how we thought about it. You can swap those letters around. You could use GMH, you could use GHM, you could use MGH, whatever you want, because, you know, I can swap them. But there is one thing that we haven't talked about before up to this point. So we know that traditionally, by the way, we write it in the order of MGH, but it does not matter. You can do it in any order that you want. The only reason we do it this way is because, remember what we said just a few minutes ago? The weight is mg. So this is equivalent to saying the weight times the height. And that's going to be the weight on whatever planet you're on, because g depends upon the planet. So this is why traditionally we're going to write this as mgh, just because it allows me to pull out that weight. Even though it's not common, we're going to use that weight. There are times when we will. so it's worthwhile. Okay, so from here on out, we'll call it mgh, just so that if we ever need to pull out that weight, we can, because the weight is mg. All right, remember though that dimensional analysis cannot give you any constants. You remember how our kinetic energy was 1/2 mv squared, and we said, okay, well that constant there doesn't have any units. So doing this kind of dimensional analysis is not going to be the constant. It's not going to give you the constant. You have to either do it by experiment or come up with some theoretical proof for this. In the case of gravitational potential energy, and we may do this later on, but in the case of gravitational potential energy, I could take another way of getting the same thing and then figure out theoretically what that particular, using theoretical methods, what that particular constant is. We're not going to go through that right now, but if you do those experiments or whatever, you're going to find that the constant is simply 1. So there's no reason to write it. But I want you to always remember is that there always is a constant. There is some constant, call it C or whatever here. It's just in this case, C is 1. There was a constant here as well, but in this case, the constant was 1/2. And we found that because of the calculus that we were doing. But we could do it by experiment or any other way. Never ever forget that there is always a constant in front of these expressions, even if we don't traditionally show it, right? We don't show it if it's 1, but it's still there, and all physics mathematical expressions have that constant in it. All right. Okay, so we're going to write down our last bit here. We need a symbol for the gravitational potential energy. Remember, for the kinetic energy, which we usually just abbreviate KE, we decided it was going to be EK. So any kind of energy of motion, something that's going like that, we're usually going to use an E for it. Any kind of stored energy, we're going to use a U. So that's a U. And by the way, for me, 2 flags is a capital V. So that's actually a U anytime you see that. And then we need to give it some sort of a subscript to distinguish it from the many types of potential energy there is. So we're going to use the symbol UG to be gravitational potential energy. That's how you read that. The U means potential energy. The subscript G means gravitational. So it's gravitational potential energy. So we're going to write our final form here. So we have gravitational potential energy is equal to mgh. Simple as that. Okay. And then as we say here, on Earth, near the surface, the gravitational potential energy is 9.81. Let me ask you this. Does it matter what the direction of the gravity is for this? Does it matter if G is positive or negative? Is the energy a vector? No, it's not. Now the energy can change. I can have, if I go from, let's say that I start here, this is the ground, and maybe I'll start at this height 1 and I'll take something up to this height 2. So maybe I take my ball and I bring it all the way up to here. So I've got a change in energy, and in that energy, that stored energy might be positive in this case because mgh2 is greater than mgh1. And so the change in my gravitational potential energy is just going to be the difference between those two. And that would be positive, right? Because it's increasing. On the other hand, what if instead of going up, I go down? Well, now this is still true, right? However, now I'm going, let me write this out. This is going to be positive because it's mgh2 minus mgh1. But now my change in potential energy is going to be negative because I've got mgh1 minus mgh2. And you see that h2 is greater than h1. Okay. If I were to put this in that same form with that parenthesis, just so you can see that, I need to swap these two. But remember, the mgh2 is subtracted mgh1. You see how that works? So if I multiply through by that minus sign, the mgh2 becomes negative, and then the mgh1 becomes positive, just like I have right here. So we see that in this case, our change in energy is going to be negative, but that's not a direction. That's simply, is it increasing or decreasing? Let's think of it as temperature. If my temperature increased, is it increasing in some X or Y direction? No, it's simply increasing or decreasing. Okay. All right. So The beauty about this is that it is not a vector. And so I don't have to worry about any kind of directions or anything. I just say, hey, it changed. And so that's good. I don't need to do anything else. So let's apply this. Take a look on the next page. So here we've got this crazy roller coaster that we're going to put our robot on. And you may need to zoom in on either on your PDF if you're looking at that, or hopefully you've printed it out because those numbers are a little bit small. So I'm going to write them larger here so that you can see it. So the mass of my robot is going to be, let's put it on the other side so I've still got room. So the mass of my robot is 1.5 kilograms. All right. This height here, x is 20 meters. At point A, which is right here, x is 17 meters. At point B, which is right here, x is 1.0 meters. This is point C, and x is, hard for me to read too, x is 13 meters. And then this is point D, x is again 17 meters. So these two, A and D, are at the same height. And then point E is down here, kind of in between. And that's going to be x is equal to 6 meters. Okay, so that's our setup. At the top of the ramp, at the top of the roller coaster, the robot's just sitting there. All right, what is its kinetic energy? Is it moving? No, so its kinetic energy is simply 0 joules. How about its potential energy, its gravitational potential energy? Well, we're going to use our new expression for that. So I know that UGH is going to be equal to, or UG is going to be equal to MGH. And so UGH is going to equal 1.5 kilograms times 9.81 meters per second. And again, I do not have to worry about any signs. And then times the height, which is 20 meters. We're going to assume all of these are 2 significant digits. All right, so if you put that in, I got that. We're going to take this with our calculator now. We're going to do 1.5 times 9.81 times 20, and I get 294 joules. Remember, we really should only keep, well, we can only keep 2 significant digits at the end. But my suggestion to you is always keep 1 or 2 more. That way you won't be rounding off too early, because calculations, like you're doing in here, they don't have precision. Precision is only about measurements, so we never take significant digits from a calculator with that. So, and if you wanted to go to 4 significant digits, I got 294.3. As long as you're at least 1 more significant digit than what you're going to keep at the end, most of the time you're going to be fine. If you keep 2 more, you're definitely going to be fine. All right. So this is going to be up here. I'm going to have 294 joules. So now we'll find the total energy, the system energy of the robot. You simply add them together. I'm pretty sure you can do that one, right? So that's simply going to be 294 joules. Now here's the thing. The robot must have 294 joules everywhere as it goes down the roller coaster. That doesn't change. Why? Because system energy is conserved. So the total system energy, in this case that's just the robot, must be conserved. All right. So now suppose the robot is at point A. So it's at that x equals 17 meters. We want to know what is its velocity. Okay. What I want you to do now, think about what we've talked about. Pause the video and see if you can figure out a mathematical expression, a mathematical way of figuring out what is that final velocity. I'll give you a hint. You can't use kinematics on this, right? Because I'm moving in 2 dimensions, and we haven't learned how to do kinematics in 2 dimensions. So think about what we've been talking about. Pause the video. Did you think about it, or are you just waiting for me to tell you? Really can't stress how important it is that you take the time to process this. I'm only going to ask you to do that when it really matters, when it's about bringing that into your long-term memory. If you aren't doing this, you're actually going to make it harder for yourself when you're trying to take the exam, even when you're trying to do the practice problems for homework. So really, really take my advice. Yes, if you're doing this online, you may say, oh yeah, I'm just going to let it go. That's not going to help you learn it. So we've got to be able to interact with the material. Okay, well, we're going to do conservation of energy. And we've talked about briefly how we were going to do this, but here's the technique that I want you to use every time. So we write down every type of energy that might be in the problems. And all of this is system energy. So if I have more than one object, then I'm going to have UG, for example, for each object. We've only got one right now. And so I know that the robot could also have kinetic energy, and it will have at any point, so at this point it's point A, that total has to be the same. I can trade them back and forth, but the total has to be the same. So what you can do then is, since this is the total energy, we've already calculated, we already know that's 294 joules. And so you might say, well, I'm just going to put 294 joules here, and that's fine. What I want you to think about, though, is how we might set this up, though. At the start of its motion, right up here at the top, does it have any kinetic energy? No, right? It's not moving, so that's 0. Can we find the gravitational potential energy? Sure, right? That's that mgh that we did right here. So I've got everything the robot has right now is gravitational potential energy, and that's exactly what you decided here. You decided that both of these together was going to be my total energy, and guess what? The kinetic energy was 0. So this is exactly what you knew instinctively had to happen, but we're doing it mathematically. Now, when I get down to point A, do I have any kinetic energy? Sure, he's moving. Do I have gravitational potential energy? Sure, I'm not on the ground, right? I'm still up above, so I've still got some stored energy in there. Is that gravitational potential energy at point A, is it greater than, equal to, or less than the gravitational potential energy I had at the start? Well, it's got to be less, right? Because I transferred some of that energy into kinetic energy, because it's a reversible process, like we talked about at the beginning. I can take kinetic energy and put it back into gravitational potential energy. That would be me coming back up the track, as we're going to see in a minute. Or I can take that gravitational potential energy, convert it into kinetic energy. That's me going down the track. All right, so the next step after this then is always start with it in this form, because it will help you think about what's going on. We might have springs, we might have heat, we might have all kinds of things going on. So then go back with your flip book, as we've said at the beginning, and put in your equations. So I know that this is mghi, because my mass didn't change, my gravity didn't change, not over the course of the roller coaster, is equal to mghf plus, and then gravitational potential, or kinetic energy is 1/2 mvf squared. Notice as I try to solve this, so that's basically my step 4 right there, right? So I've got all of this in here. I've defined my symbols in step 3. I'm ready for my step 5. So let's do that. I've got mghi is equal to mghf plus 1/2 mvf squared. So we're going to solve this for vf, because that's my goal, is to find vf. So vf, and I cannot do it as a vector, that's an important thing. Vf is equal to my double question marks, and it has units of meters per second. All right, well, so we start looking at this. First thing we see is all those masses cancel. So this tells us something interesting. The mass of the robot doesn't matter in how fast it is at any given point. Well, we've kind of already experienced that, right? When we talked about dropping two things and they're going to hit at the same time, because the acceleration due to gravity is the same and kinematics doesn't involve mass. Same thing is true for energy. Even though both terms involve the mass, because the mass didn't cancel or didn't change, they're going to cancel out. And so I could take a big heavy robot, I could take a little small robot, and they're going to be exactly at the same speed by the time they get down to point A. All right. So let's continue to solve for VF. I'm going to move this term here to the other side. And so I get GHI minus GHF is equal to 1/2 V squared. Factor out my G, and I get HI minus HF equals 1/2 VF squared. Move my 2 over here, I get 2 HI minus HF equals VF squared. And then finally take the square root of both sides. And so I get 2G HI minus HF is equal to VF. Notice that this is not a vector. We found the speed, but we've not really found the velocity, and that's because the velocity is at some angle, right? I'm not just falling straight down. Okay, so this gives me what I need. So now we're going to plug in our numbers, and so we know that 2 times 9.81 meters per second squared times my initial height was 20 meters minus my final height is 17 meters. Pick up your calculator. Let's do that. So we're going to have 2 times 9.81 times parenthesis 20 minus 17, or you can probably do that in your head. And then I get 58.86, but I still need to take the square root. And so I get that the final velocity then is 7.67 meters per second. And since I can only keep 2 significant digits at the end, that tells me that my final velocity is really 7.7 meters per second. And so we'll put that here, 7.7 meters per second. And did the velocity depend upon the mass? No, actually it does not matter in the slightest. All right. Now, if we had done this with kinematics, if I were just falling straight down, I would get a very similar result. And we'll do that kind of thing later. But what I want you to do now is go to the next page. Now that you've got your expression, your equation, it's going to be very easy for you to find the rest of these values. So just to remind ourselves of what that looked like, we said that VF was equal to the square root of 2G HI minus HF. Okay, let's set up the one at point B, and then we'll go, and then I want you to work out all the rest of them. You may need to go back to the previous part of the video to see the numbers where I've written those in, or if you've got your page, you can kind of zoom in on it and see what you've got. But at point B, if we want to know VF at point B, then it's going to be the square root of 2G. That's not going to change. My initial height was still 20 meters. My final height now, though, at point B is 1.0 meters. Figure it out. Go through and get the rest of your values, and then I'll tell you what I got, and we'll see how that goes. Pause the video. Do it now. It's good practice. You got them all? Now, one important thing to keep in mind is, notice that my HI was 20 meters every time. It's not from the previous one. Can you think about why? Like for point B, it wouldn't be from point A. Because the total energy has to be the same. Now, I could do it from point B, or from point A to point B. Let's see how we can do that. UGI in this case would be my gravitational potential energy at A plus, let's make that kinetic, plus my kinetic energy at A must equal my potential energy at B, gravitational potential energy, plus my kinetic energy at B. And in this case, none of these are zero. However, you have absolutely everything that you need. We could say mgh at A plus 1/2 mv at A squared must equal mgh at B plus 1/2 mvb squared. You already know VA. You just found it in the previous problem. So we could rearrange this equation and solve it for VB, and we'll still get it. However, that's a lot of work, isn't it? So why not go back to your original expression? But to do that, you have to remember that that HI right there, what that's physically telling you is that's how much energy I've got. That's what's giving me my energy, because initially it was nothing but kinetic energy. I'm sorry, it was nothing but potential energy from that point. Okay, so here's the numbers that I got. You can check them. I got 19.3 meters per second, 11.7 meters per second. Point D, I got 7.67 meters per second. Remember, you should be doing all these to 2 significant digits. I'm giving you the third one so that you can see if you had any rounding issues or anything like that. Interestingly, point D it's got exactly the same velocity that it had at point A. And that's because, if you remember, it's coming down like this, and I had my point A, and then I went all the way down here. And as I started back up, I was at the same height. Does that make sense? Does that make sense physically? Think about it. So let's just say I had just a bowl, and that was it. So I started here, and about halfway, I've converted half of my gravitational potential energy into kinetic energy. I come down to the bottom, and now let's say that it's on the ground, just to keep things simple. I've converted all of my gravitational potential energy into kinetic energy. As it starts to go up, now I'm converting kinetic energy back into gravitational potential energy. So when I'm at exactly the same height that I was over here, half of it will have been converted if I'm halfway there. You see how that works? So yeah, it makes sense. I'm just trading energy back and forth because it's a reversible process. When we talk about deformational energy, we talk about work done by friction. Those are not reversible processes. Once you get those irreversible things, that energy is just gone. And this is actually why if you have a bowl, right, and you start a marble and you just let it roll, right, eventually it's going to come down here and stop. That's because there are dissipative losses. Air resistance, sure, but not much. It's mostly friction. So every time I'm losing energy to friction, well, that means I don't go quite as high as I did before. And then I don't go quite as high because I'm losing that energy. So I can't get all the way up to my original gravitational potential energy because some of it was lost. Eventually, all of it has been lost, and the marble is just going to sit down here at the bottom from that with no kinetic energy and no gravitational potential energy. And this is why it's not possible for the marble to just stop right here on the edge. It's still got gravitational potential energy. Okay. All right, so the velocities then between point A and D, then they are the same. Okay, and then our last one for point E, I got 17.2 meters per second. And then again, just as a reminder, I'm giving you 3 significant digits here so you can kind of check to make sure you don't have a rounding issue. But when you're reporting these, we only have 2 significant digits worth of measurement. So this would be 19, this would be 12, this would be 7.7, and this would be 17. All right, so let's take a look at the very last page here. We're going to do one thing that's just a little bit different. So we've got our same roller coaster, all right? But suppose near point C, which reminding you, point C, let me just kind of sketch our roller coaster here so that you don't have to go back on the page. So we came down, we had a little hump, and then we came down, maybe not quite like that, that would be scary, and then back up, and then came down. I'm just trying to fit it into my camera here. And so this was B, C was about halfway, right? D and A were at the same heights, and then E was somewhere down here, okay? So let's suppose at point C, so I've been coming down like this, right? And I'm coming up here. So suppose at point C, we turn, just prior to that, we turn on the robot's motors because to give it a little more oomph as it goes up. We're going to do some work. Those motors are going to do some work. And we'll say that the motors do 45 joules of work. How fast will the robot be moving at point C? Pause the video, see if you can set up it. I'll give you a hint, it's conservation of energy. But now you've got this extra term of work. Figure out where you're going to put it. Pause the video and work it out. This is a very, very important problem. You got to start on it, or you're like, I don't know, Dr. K, right? No, you can totally do this. All right, so we're going to start out then with our gravitational potential energy. All right, I'm going to find my picture so that we're all on the same page here. Here we go. All right, so remember, write down all those forms of energy. So we know that our UGI plus our EKI must equal our, well, let's put them in the same order. It doesn't really matter. UGF plus EKF. So we know that's true, right? However, we are also adding some work into the system at this point. If we're adding work, what is the sign of that work? Well, if work is going into the system, it's going to be positive. Now, if you're using the sign conventions, so if you have a positive work, energy is going into the system. If you have a negative work, energy is coming out of the system. If you're using these sign conventions, you must put them on the left-hand side here, on my initial side. The way I think of it, I think of work as being just a scalar, not positive, not negative. or anything like that. But I say if work is coming into the system, I'm going to put it on my initial side. If work is coming out of the system, I'm going to put it on my final side. And we talked about that with deformational energy a little bit. For example, pausing what we're doing with this problem. Okay, if I did have some work lost to friction, we're assuming that that's very small for this one, but it actually is there. I would say I'm losing work here, right? So that's why I've got it on that side. However, if you think about what that means physically, this is why I like this. It makes more sense. This is my total energy that I started out with. That has to equal all three of these, right? Which means my kinetic energy is going to be less than it would have been otherwise, because I may be at this same gravitational potential energy that I've dropped down to, but some of what would have been in my kinetic energy has now gone into work. And so my total kinetic energy has to be less just to keep the total system energy the same. So that kind of makes more sense to me. I can look at it physically and I can say, oh yeah, okay, this is how much I started with, sure, but I lost some work here. So my total then means I've got this amount of energy and then plus some work, so to keep these two things equal. All right, in this case, we're ignoring friction. However, we do have some work being done by the motors. So if that's going into the system, then I would put it over here. So we're going to say work done by the motors, like that. The reason I do it that way is now I see I have more energy to start with than I had originally. And so I'm going to get a little extra kinetic energy out of this. I'm going to get a little bonus out of that. Does that make sense? All right, so let's put in our expressions, our mathematical expressions. Always set it up this way, because this way you can look at it conceptually and say, oh, okay, I see what's going on. If you try to go straight to putting in the mathematical definitions for each of these, you're going to lose some factors. That's going to be hard to keep up with. All right, so I don't know the work done by my robot as an expression, but I do know how much that is. It's actually just a number, right? That's just 45 joules. All right, I know my initial then is going to be mg, we'll call that I, and that's going to be at the top of the ramp up here. So that's at my 20 meters. And then what was my initial kinetic energy? Well, that was 0, right? Because I started from rest. Didn't have to, but in this particular problem, we started from rest. So that's going to be a 0. I won't even bother writing the 0 there. You should be able to see that. And then that's going to be equal to mg, let's make that clear, that's not a subscript, mg, and we want h at point C, plus my kinetic energy at point C squared, so Vc squared. Okay. All right, I know everything that I need, because I know hc, I know hi, I know wm, I certainly know my masses. Notice that the mass does not cancel in this case, right? That's going to tell us something useful later. The amount of energy I get actually is going to depend upon the mass with the motor. So, and if you think about it, that makes sense. The motor has to work harder to push something that's got more mass. So my mass does not cancel. I cannot get rid of it in this particular case. All right. So what I'm going to do then is I'm going to solve this for Vc. So I'm going to move everything over to the other side just to start off with, plus mghi minus mghc is 1/2 mv squared. Do not plug in numbers until you have what you want equal to symbols. Never, never, never. The odds of you making a mistake when you do that are very high, and it's almost impossible to figure out where you did it. Okay. So I'm going to factor out an mg here. So I've got Wm plus, actually let's do one thing before we do that. Let's go ahead and divide out my m's. So remember, when we divide by something, we divide each term by that. Never ever, divide the m here. Never ever just draw a big fraction bar here and put your m in the bottom. Never. Always divide each term, because what you see when you do that is a lot of things cancel out. Right, I'm just left with a g here. That's a g, I promise. If you had put just one big giant bar here, you wouldn't have things cancel out. And so you're going to make your job a lot harder. So let's rewrite what we've got here. I've got Wm over the mass, so the work done by the motor over the mass, plus GHI minus GHC is equal to 1/2 Vc squared. Now I'm going to factor out that G. And so I get Wm over m plus GHI minus HC is equal to 1/2 Vc squared. I need to divide by 1/2 or multiply by 2. They mean the same thing. And so I get, I'm just going to do this whole thing here, 2Wm over m plus, actually no, let's still do it term by term, just so that we're maintaining the habit. 2GHI minus HC is equal to Vc squared. And then the last thing is just to take the square root. So I'll do that over here. So I get the square root of 2Wm over m where did it go? Plus 2GHI minus HC, and that is equal to, finally, our velocity at c. And so this is almost, let's look at what this means physically. This is almost what I got before, isn't it? Before I just had this term right here. But now I'm getting some extra velocity because my robot is adding some work in here. It's putting some energy into the system. Well, that makes sense then. I'm going to go faster as a result of that. So physically, this all makes sense. All right. So what you should do then, now that you have what you want equal to a symbol, you would go ahead and you plug in those numbers and you'd see what you get. So we get 2 times 45 joules divided by, I believe, forgotten the mass of the robot, I believe it was 1.5 kilograms. Let's make sure before we get too far. Yeah, 1.5 kilograms. Plus 2g, and then hi in this case was 20 meters. And we decided hc, again I need to go back and look at my notes because I don't remember, hc was 13 meters. That looks like a plus. Let's make that not look like a plus. There we go. And that's it. Plug all that in, take the square root, and you've got your final answer, and you're good to go. So now we've explored the concept of gravitational potential energy, and it's honestly not all that complicated. You may have seen it in high school, but one way or another, you probably have a pretty good idea of if I pick something up higher I go, the more energy is going to be in that, and then I get that out of kinetic energy. There are 2 new things in this that you need to keep in mind. First and foremost is how we came up with the equation in the first place. Now, the equation itself was simple, and that's why we started with this method with something that is simple. But we thought about what terms might be involved in the equation, and then we decided, are they directly proportional or are they inversely proportional? Based on that, we were able to get our equation, except for a constant. And remember that the constant, there is no way for you to get that from just looking at the units. You've got to either do an experiment, which is common, or you look at the theoretical derivation and see if from that you can actually figure out, okay, is it a 2 or 1/2 or whatever. Very often in engineering, though, you're going to get what's called a polynomial expansion. So we'll know that this crazy function like this is going to depend upon a certain coefficient times x squared plus a certain coefficient times x plus a certain coefficient times x cubed, and then maybe just a constant value at the end. And we might have expressions all the way up to, x to the 6th. Those coefficients in front of those are our constants, and they're usually just simply found by experiment with that. So that's not uncommon at all. In this case, we found that the constant was 1. But it's very important that you keep in mind that there is a constant there, always. We just don't show it if that constant is equal to 1. And then the other thing that we talked about was this idea of kinetic energy and gravitational energy being a reversible process. Remember the roller coaster? We could trade it back and forth without losing anything. As soon as I add in a dissipative loss, work due to friction or deformational energy, anywhere where the energy basically leaves the system, it's not destroyed, it's there, I just can't find a way to measure it. There's no way for me to reverse that. And so that changes things considerably with that. So as long as you're keeping those concepts in mind and think about just writing out conservation of energy, all of those individual symbols, then mark out which ones are zeros, and then go to your flip book and find the expressions, the mathematical expressions for each one of the ones that remain. That's the technique we're going to use for a long time, pretty much any time that we're working with energy. We'll see you next time.